Describe the process of conducting a univariate analysis on a given dataset. Include the steps involved and the key metrics you would evaluate. Conducting a univariate analysis involves examining a single variable within a dataset to summarize and find patterns in the data. Here's a step-by-step guide on how to perform a univariate analysis. 1. Data collection. Begin by collecting the data you intend to analyze. This data could be from a database, a CSV file, surveys, or any other source. 2. Data cleaning. Prepare the data for analysis by cleaning it. This includes handling missing values, removing duplicates, and correcting errors. This step ensures the quality and accuracy of your analysis. 3. Exploratory data analysis. Start with exploratory data analysis by focusing on the single variable of interest. This can be done using both graphical and non-graphical methods. 4. Graphical analysis. Histograms, useful for showing the distribution of numerical data. Bar charts, ideal for categorical data to show the frequency of each category. Box plots, good for spotting outliers and understanding the spread and skewness of the data. Pie charts, useful for displaying the proportion of categories in a more visually appealing pie format. 5. Descriptive statistics. Calculate key metrics to get a deeper understanding of the data. For numerical data, mean, the average value. Median, the middle value in the data set which divides the data into two halves. Mode, the most frequently occurring value. Standard deviation, measures the amount of variation or dispersion in the data. Variance, the square of the standard deviation. Range, the difference between the maximum and minimum values. Quantiles, values that partition the data into equal-sized subsets, e.g., quartiles. Skewness and kurtosis, metrics that describe the shape of the distribution. For categorical data, frequency counts, the count of each category. Mode, the most frequent category. 6. Data interpretation. Interpret the results of your graphical and statistical analysis. Understand what the measures of central tendency and variability tell you about the data. 7. Reporting. Compile your findings into a report. Include visual aids like charts and tables along with descriptive text to explain the insights from your analysis. This report should be comprehensible to someone who may not be familiar with technical statistical terms. 8. Decision making. Use the insights gained from the univariate analysis to make decisions or to inform further research. This might involve identifying areas for operational improvements, focusing on certain segments, or planning further detailed analyses. This structured approach to univariate analysis helps in understanding the basic properties of a single variable, which can be crucial for further multivariate analysis or for deriving actionable insights from the data. Explain the use of scatter plots in bivariate analysis. Provide an example of how a scatter plot can be used to identify relationships between two variables. Scatter plots are a fundamental tool in bivariate analysis, used to visualize the relationship between two quantitative variables. They help in identifying patterns, trends, correlations, and potential anomalies between the variables. Here's an explanation of how scatter plots are used in bivariate analysis, along with a practical example. Use of scatter plots in bivariate analysis. 1. Visualizing relationships. Scatter plots display individual data points on a two-dimensional plane, with each axis representing one of the variables. This setup allows you to visually assess the relationship between the two variables. 2. Identifying correlations. By observing the pattern formed by the data points, scatter plots can help determine if there is a correlation between the variables. If the points trend upwards, from left to right, it suggests a positive correlation. If they trend downwards, it suggests a negative correlation. 3. Assessing linearity. Scatter plots are particularly useful for checking the linearity of the relationship between two variables. A linear relationship will appear as a roughly straight line of points. 4. Detecting outliers. Any data points that do not fit the general pattern of the scatter plot can be identified as outliers. These are important for statistical analysis as they may indicate data issues or special cases. 5. Understanding the distribution. The spread of the data points can give insights into the distribution and variance of the data, indicating how tightly the variables are related. Example of using a scatter plot. Scenario. Let's say you want to analyze the relationship between the number of hours studied and the scores achieved by students on a test. Steps. 1. Collect data. Gather data on the number of hours each student studied and their corresponding test scores. Create a scatter plot. Plot the number of hours studied on the x-axis and the test scores on the y-axis. Each point on the plot represents one student's data. 3. Analyze the plot. Observe the pattern formed by the points. If the plot shows an upward trend, it suggests that higher study hours are associated with higher test scores, indicating a positive correlation. 4. Linearity and outliers. Assess whether the data points form a straight line, which would suggest a linear relationship. Also, look for any outliers, such as a student who studied very little but scored highly or one who studied a lot but scored poorly. Interpretation. From the scatter plot, educators can deduce if additional study time generally leads to better test results, which can inform teaching strategies, study recommendations, and student guidance. Moreover, outliers can be further investigated to understand unique cases or anomalies. Scatter plots thus provide a clear, intuitive way to visually analyze and interpret the relationships between two variables, making them indispensable in statistical analysis and decision-making processes. Explain the concept of dispersion in univariate analysis. Discuss the different measures of dispersion and their significance. The concept of dispersion in univariate analysis refers to the spread of values around a central point, like the mean or median, within a data set. It provides insights into the variability or consistency of the data, which is crucial for understanding the reliability and predictability of the data. Dispersion helps in assessing the risk, quality control, and decision-making processes in various fields. Measures of dispersion. Several key measures are used to describe dispersion in a dataset. 1. Range. Definition. The difference between the maximum and minimum values in the dataset. Significance. It gives a quick sense of the spread of the entire dataset but is sensitive to outliers as it only considers the two extreme values. 2. Interquartile range. IQR. Definition. The difference between the 75th percentile and the 25th percentile of the data. Significance. IQR provides a better sense of the spread of the middle 50% of the data, which is less affected by outliers and extreme values. 3. Variance. Definition. The average of the squared differences from the mean. Significance. Variance gives a comprehensive picture of the spread of all data points around the mean. It's very useful in statistical analysis but its units are squared, which can be difficult to interpret directly in context with the data. 4. Standard deviation. Definition. The square root of the variance. Significance. Standard deviation is one of the most commonly used measures of dispersion because it is in the same units as the data, making it easier to interpret. It indicates how much on average the values in the dataset deviate from the mean. 5. Mean absolute deviation. Definition. The average of the absolute differences from the mean. Significance. This measure provides a clear picture of variability without squaring the deviations, which can be more intuitive and less sensitive to extreme values compared to variance. Significance of dispersion measures. Understanding dispersion is crucial for several reasons. Risk assessment. High dispersion indicates higher risk and unpredictability in the dataset. For instance, in finance, a higher standard deviation in stock prices suggests more volatility and risk. Quality control. In manufacturing, low variability, low dispersion, is often associated with high quality as products are consistently close to some target value. Comparative analysis. Dispersion measures allow comparison between different datasets or groups within a dataset to understand which group is more varied. Data modeling. Effective modeling requires understanding the underlying variability in the data. Dispersion metrics can influence choices about the types of statistical models or tests that are appropriate for the data. Dispersion provides a more nuanced understanding of the data beyond central tendency, mean, median, mode, offering essential insights into the spread and reliability of the data, which are fundamental for interpreting results and making informed decisions. Discuss the various stages of EDA and the tools and techniques commonly used in each stage. Exploratory data analysis is a critical step in the data analysis process, aimed at understanding the main characteristics of the data, discovering patterns and anomalies, and formulating hypotheses. It typically involves a series of stages, each using specific tools and techniques. Here's an overview of these stages and the common tools and techniques employed. 1. Data collection. Tools, techniques, data sources, collection from databases, surveys, and other data-generating sources. Data importing tools, libraries like pandas in Python, data table in R, or software like Excel and SQL databases for importing and initial handling. 2. Data cleaning. Tools, techniques, handling missing values, imputation techniques, or removal of missing data depending on context. Dealing with outliers, statistical methods for outlier detection, Z-score, IQR. Data type conversions, ensuring correct data types for analytical compatibility. Data transformation, normalization, scaling, or transformations to meet the assumptions of various analytical tools. 3. Data profiling. Tools, techniques, summary statistics, mean, median, mode, range, variance, etc. Data profiling tools, pandas, describe, Python's pandas profiling, or as summary, functions. Data visualization, initial plots to understand distributions and existing relationships, histograms, box plots. 4. Data visualization. Tools, techniques, univariate visualization, histograms, box plots to understand the distribution of individual variables. Bivariate visualization, scatter plots, crosstabs, and bivariate line charts to explore relationships between pairs of variables. Multivariate visualization, heat maps, parallel coordinates, and 3D plots to understand interactions among multiple variables. Visualization libraries, Matplotlib, Seaborn in Python, ggplot2 in R. 5. Data transformation and feature engineering. Tools, techniques, variable transformation, log, square root, or binning techniques to modify the scales and distributions. Feature creation, deriving new informative features from existing data using domain knowledge or data-driven methods. Dimensionality reduction, PCA, principal component analysis, TSNA for reducing the number of variables while retaining essential information. 6. Correlation and causation analysis. Tools, techniques, correlation matrices, to quantify and visualize the linear relationships between variables. Causation insights, careful interpretation of data to hypothesize causal relationships, possibly guided by domain expertise. 7. Hypothesis testing. Tools, techniques, statistical tests, t-tests, chi-square tests, ANOVA to validate hypotheses about the data. Confidence intervals, estimating the uncertainty of an estimated parameter. 8. Iterative analysis. Tools, techniques, iterative modeling, refining hypotheses and models based on initial findings and further explorations. Advanced visualizations, more complex graphical representations as new questions and hypotheses arise. Commonly used software and libraries, Python libraries, pandas, NumPy, SciPy, Matplotlib, Seaborn, Plotly. R packages, dplyr, tidyr, ggplot2, caret. Data visualization tools, Tableau, Power BI for more dynamic and interactive visual explorations. Each stage of EDA is crucial for ensuring that the subsequent statistical analysis or machine learning modeling is based on a thorough understanding of the data's underlying properties and relationships. This approach helps to maximize the effectiveness of the predictive models and insights derived from the data.